try to focus a little bit more, more quickly into chapter 9, which is really similar to chapter 8. It just extends it and adds a few things about sulfur compounds at the end. But we basically looked at the structure of a simple alcohol. Although I should point out that there are alcohols that are not so simple. In particular, if you have an alcohol group attached to a benzene ring, that's in a slightly different category from simple alkyl alcohol. This molecule is a very common one. It's called phenol. It used to be used as a topical antiseptic. It's used to make now mostly resins, phenol formaldehyde resins that you may have heard of. That's an alcohol, but because the OH group is attached to this unusual benzene ring, which we'll study next term, its properties are slightly different, in some cases very different, and one of the differences is in terms of acidity. And that's really the first thing I want to talk about this morning, not only with alcohol, but with organic compounds in general. Acidity is a big deal in organic chemistry, but it takes a different framework from what you have in freshman chemistry, where you talk always about acids and bases in water. In an organic compound, you have a lot of hydrogen. And you know that acidity traditionally involves a proton, or H plus, being lost from a molecule, like HCl, or sulfuric acid, or phosphoric acid, donating a proton. That's the classical Lowry-Bronsted definition of acidity as a proton donor. Organic compounds are very reluctant proton donors because the hydrogens are very tightly bound to the molecule. But you can divide hydrogens conveniently into three types. One type has hydrogens attached to a heteroatom. That would be something other than a carbon. In particular, an oxygen, a nitrogen, or a sulfur. So ROH has a hydrogen attached to oxygen. Organic chemists look at that as an acidic hydrogen, even though in the broader context of chemistry, alcohols are no more acidic than water. And most people don't consider plain water to be an acid, but because it's so rare for organic molecules to give up protons, the fact that this does it at all is taken very dramatically and seriously. So if you have a hydrogen attached to
run up the hill?
an O or an N or an S, and remember oxygen takes 2 bonds, nitrogen takes 3,
Am I going to slip and fall backwards?
sulfur takes 2.
Slip
What I have with there is an alcohol, an amine in the middle, and a thiol in the bottom, THIOL. But these are all acidic hydrogens. So with some suitable base, to me, as an organic chemist, I look at that hydrogen as being able to be removed as a proton with a suitable base. Suitable would be a base strong enough to do this to the extent that I want that done. This could be, of course, in equilibrium. And the same for the amine. nitrogen or a sulfur. That is very doable and a very important reaction in biological chemistry. Often the removal of a proton triggers a very significant chemical event. It does technically just convert the starting compound into a salt. So for instance, if I take methanol and I treat it with a strong base, or even a weak one, let's say potassium hydroxide, which is not that strong a base as far as alcohols. So methanol and KOH have the ability to react where the base, a hydroxide ion from the KOH, pulls a proton off the OH of the methanol. Now, it's not going to touch any of the hydrogens on the carbon, because those kinds of hydrogens are in a whole different class. They're very rarely removed as a proton. But this would produce an equilibrium where you have some of, instead of the potassium salt of water, which is what KOH is, you have an equilibrium with it, the potassium salt of the alcohol plus water. So this is a simple acid-base equilibrium, and it's really a competition between the acidity of the methanol OH and the acidity of water. Since they're about the same acidity, if you put KOH in methanol, you do get an equilibrium. And you would not be able to produce very much of the potassium salt of the methanol unless you had a very large excess of the methanol. And of course, that would push the reaction to the right. Now, these are, again, acidic hydrogens. The types of hydrogens that are not acidic generally are the other kind of hydrogens you see in organic molecules, those attached to carbon. Those would not be acidic. Now, having said that, as we march along through organic chemistry and start looking at a lot of reactions, you will begin to see some types of CH hydrogens that, difficult as it may be, can be removed as a proton. So CH hydrogens can be acidic enough so that with a heroically strong base, you can effectively pull a proton off a carbon. Now, why is it so difficult to pull a proton off a carbon relative to oxygen or nitrogen or sulfur? What would you think would be a glaring reason for that? Well, what's the problem with pulling a proton off an atom? Well, yeah, if something's difficult to do chemically, it's because it's producing something unstable. What's unstable about pulling a proton off an atom? What are you causing? What problem are you causing for that atom that's losing the proton? You're causing it to sit there with more electrons than it would care to sit with, like O minus or N minus or S minus or C minus. Those atoms don't like to have that many electrons. That's an excess of electrons. They like to be neutral rather than charged. So why is it harder to pull a hydrogen as a proton off carbon than it is off oxygen?
Maybe oxygen is more electronegatively dense.
Right. It's bigger, it's more electronegative, and it can take the hit better than carbon. It's all about stability. And these things should make sense in your head. Chemistry doesn't make sense to you, you'll never be able to use it or deal with it. And almost all of chemistry at its root is as simple and dumb as a hammer. It's, chemistry is really very simple, but people over-analyze it or think that I'm never going to figure that out, so my brain isn't even going to tackle it. Don't be afraid to think. The difference is in the size of the atom that has to sit with the negative charge once the proton is gone. That thing that has to sit with a negative charge, in freshman chemistry you learn is called the conjugate base. And acidity is entirely controlled by how stable the conjugate base is once it's produced. Strong acids produce stable conjugate bases. Weak acids don't produce stable conjugate bases. Now, carbon is a small atom. Now, you might say, well, it's not that much smaller than nitrogen or oxygen, but that would again be overanalyzing. You're thinking that your brain can make that judgment. How big or small a difference is, you have to be careful, is really not analyzable by your brain just sitting there. The difference between carbon and nitrogen, even though it looks small because they're right next to each other on the periodic table, in terms of acidity, it's enormous. And oxygen is so much better at handling a negative charge than carbon that it's like 1,000,000 times more acidic. Now, as I mentioned, you will see some types of hydrogens attached to carbon that are able to be pulled off as a proton. And that's a very valuable thing to do, as you'll see, because if you can do that, that produces a very, very useful type of carbon called a carbanion. So it's the carbon that has to sit there without the proton as a C-. The most important thing when you begin to look at how molecules get built from smaller molecules to larger ones, and that's the natural order. Not only in the laboratory, but also in nature. Biological chemistry, bigger molecules are made from smaller ones by adding carbons. Bigger molecule for organic means more carbons. How do you make new carbon-carbon bonds? A carbanion is a good way to do that because if you can pair up this type of carbon with this type of carbon, they're going to bond together easily. So carbanions are the major characters in carbon-carbon bond-forming reactions. You'll see about 6 of those kinds of reactions. And they're the backbone of organic synthesis, both in the lab and in nature. Pairing an electron-rich with an electron-poor carbon is just about the only way to make a carbon-carbon bond. So you'll begin to see some types of electron-rich carbons and some types of electron-deficient carbons. And those are the ones that will pair together. Now, the special cases where you'll see that this is possible will be where that carbon is attached to some type of strong electron withdrawing group that can bleed off that negative charge from the carbon. To get some relief to that carbon, something has to come along and draw some of that excess electron density out of there. It's like having a tire that's overinflated. You've got to bleed out some of the air. So an electron withdrawing group attached, or maybe a couple of them attached to the carbon, can make that carbon much more comfortable with a negative charge. And that's what you see all the time. Something is allowing that carbon to sit with that negative charge. And it's virtually always something that will pull electrons away from the carbon. Now here's ethyl alcohol.
See?
So when you look at a molecule like ethyl alcohol, you see a bunch of carbons, well, 2 carbons, 6 hydrogens, and an oxygen. The hydrogens there are to be thought of as initially being acidic or not acidic. As an organic chemist, I've come to look at molecules initially that way. I may not actually do anything with that acidity, but look at a molecule, and if I see acidic hydrogens, I make note of them. The most acidic hydrogen in this molecule is that one. Hydrogens attached to carbon are always less acidic than hydrogens attached to oxygen or nitrogen or sulfur. And there's a gap as wide as the Grand Canyon between hydrogens on oxygen, nitrogen, or sulfur, and hydrogens on carbon. Even in cases where those hydrogens on carbon have electron withdrawing groups that allow me to heroically pull a proton off them, there's still a big difference. That's another category, lower acidity. Now, the way this acidity plays out is that, first of all, it allows you to produce these anions, and you know that an anion is electron rich with at least one non-bonding pair of electrons. This oxygen has 3, so it's a nucleophile and a Lewis base. So this is a way of producing very aggressive nucleophiles and Lewis bases. The ethoxide ion is a good nucleophile and a good base. Now, there's another reason for this being important, because if you can remove that hydrogen as a proton, the ability to oxidize an organic compound is half completed. Oxidation and reduction is part of this chapter 8. Now, don't panic, we're not going to do these nasty redox reactions that you get in freshman chemistry. Organic chemists have a very practical definition of oxidation. Oxidation is any reaction that removes hydrogens from an organic molecule. It's actually a little more complicated than that, but, and the general symbol is just bracket O.
Can I see to make sure that I copied everything right? I can't see some stuff. Thanks.
It's a reaction that removes hydrogen, and sometimes it also adds oxygen, or sometimes the hydrogen count remains the same, but oxygen is added. So it makes sense that adding oxygen would be an oxidation, but also removing hydrogen is, and sometimes you get one or the other or both. So if I remove this hydrogen and this hydrogen here, you get a pi bond to form between that carbon and oxygen. So if I rip out those 2 hydrogens and slip in a pi bond, I oxidize the alcohol to an aldehyde. The aldehyde is a higher oxidation state than the alcohol. Notice I've lost hydrogen, lost 2 hydrogens. Having that OH as an acidic hydrogen again, is half the battle. So what you find in oxidation reactions of alcohols is that the OH hydrogen is lost, and then a hydrogen from an adjacent carbon. And that creates this very, very ubiquitous functional group, the carbonyl, the C double bond O. So secondary alcohols oxidize to aldehydes, primary alcohols. You have a secondary alcohol, like isopropyl, and you remove the OH and the CH, you get a ketone. So the oxidation of secondary alcohols also produces a carbonyl, but again, it's by this loss of the OH and the CH right next to it. And it is the acidity of that OH that starts the whole thing off. There are oxidizing agents that will go after that OH, react with it, and then facilitate the removal of the other hydrogen. And in the middle of that chapter 8, there is a humongous discussion of the details of this, including various oxidizing agents and how they work, etc. Don't worry about that at all.
Little one.
There is an oxidizing agent for every alcohol, primary or secondary. Now, there aren't any oxidizing agents for tertiary alcohol because they can't do this. Loss of 2 hydrogens.
For a tertiary alcohol, undergo
See, there's no hydrogen on the neighboring carbon, so it can't lose that second hydrogen. You can make a salt from it, O minus. You can lose that OH hydrogen, but you can't lose the second one. So the tertiary alcohol can do its normal thing as a proton acid, but it can't oxidize. But very, very important is this oxidation here is.
So primary and secondary alcohols, acidic hydrogen can be only the one that's neighboring.
Well, in an oxidation reaction, the primary alcohol can lose both the OH and a CH right next to it, which is a C double bond O compound. Tertiary alcohol can only lose the OH, so it can't oxidize. That's not an oxidation. Okay, and probably the central component of biological chemistry is this type of oxidation. Alcohols to carbonyl compounds, and then carbonyl compounds back to alcohol. Now, reduction is the opposite of oxidation. You just say bracket H for reduction. That's exactly the opposite of the oxidation. It doesn't remove hydrogen, it adds hydrogen, and or not adding oxygen, but removing oxygen.
Does it say ox or O plus? Listen. Just oxygen?
Removes oxygen.
That's it, just oxygen? What did he write ox? Oh, wait. Why didn't you just write O? Thanks. But there was like a plus sign or an H.
Okay, so in summary, if you take ethyl alcohol and use an appropriate oxidizing agent, there are hundreds of them available. You can pull off the OH and a CH right next to it, producing the C double bond O in its place. You can also, with different chemistry, add those 2 hydrogens back, one to the oxygen of the carbonyl and another to the carbon of the carbonyl. Now, this isn't a reversible process because it's a whole different reaction with a different reagent. We have oxidizing agents and we have reducing agents. But if you have, like acetaldehyde, you can reduce it to ethyl alcohol. If you have ethyl alcohol, you can oxidize it to acetaldehyde.
What's that?
Now, since we're looking at ethanol, of course, this is how your body metabolizes ethanol.
Your body.
The oxidizing agent would not be something like sodium dichromate, like we use in the organic lab, but it would be an enzyme. It would be an oxidase, as biochemists call it. That enzyme would do exactly the same thing as the inorganic oxidizing agent that chemists have concocted because we don't have those enzymes. Enzyme chemistry is almost non-existent in the laboratory. Occasionally, there are commercially available oxidases and reductases that you can buy, or extracts from natural products like foods that you can extract an oxidase or reductase to do these reactions. But generally, the lab is one thing and organisms are another. Organisms do their stuff more elegantly with enzymes that are whole systems for getting the reagent to the reactive site and shepherding the reaction through the process. But it's the same thing in the end. Removing two hydrogens from ethanol, the body would produce acetaldehyde. And in fact, a breathalyzer test is not a test for ethyl alcohol, it's a test for acetaldehyde, because the acetaldehyde is not a natural component in your body, nor is ethanol, but acetaldehyde is easy to test for, easier than ethanol. So if you have a large amount of acetaldehyde, it's assumed that that came from the ingestion of ethanol. The acetaldehyde even is able to be oxidized because in a water environment, water reacts with aldehydes and also with ketones, actually with any carbonyl compound. Water will actually add to a C-double-bond-O pi bond. The key to understanding how that works is very important. The carbonyl has to be viewed as a polar item. The oxygen is more electronegative than the carbon, and a carbonyl is actually quite polar. So water reacts with the carbonyl by attaching the electron-rich oxygen. So here's water. The electron-rich oxygen bonds to the electron-deficient carbon, and a proton gets transferred over to the oxygen. So OH from the water ends up on carbon, and H ends up on oxygen. And people actually call that product on the far right the hydrate of acetaldehyde. It's simply water that's clamped across the carbonyl. OH on the carbon, H on the oxygen. And it's reversible. Water goes on, water comes off. Most hydrates are actually not all that stable. They only produce a little bit of it. But notice that the hydrate is and alcohol. It's actually what we call a